All right, so we're looking at complex number, or we're starting with complex number. And this says complex number as an extension of the real number. Then I have under that I have evolution of numbers. So if you all remember anything about from number theory, you'll know that numbers start off with our understanding of numbers start off with natural numbers. So your natural numbers are your counting numbers. As you can see, the symbol is n, 1, 2, 3, 4, 5, going on to infinity. Then 0 is added. And so now, once 0 is added, we now call what? The set of numbers, counting numbers plus 0 is now called your whole numbers. You add the negative integers. Sorry, you have the negative numbers. And once you add those, you now have what? Integers. You have rational numbers. Now, a rational number is a number that can be expressed as a fraction. And so the symbol for rational number is Q, and Q is equal to N over D, where N and D are elements of the set of integers, and D is not 0. So let me start by asking a question, or let me pause here to ask a question. Why is it that the denominator of a fraction must never ever be 0? So anybody can take that one. Why is the denominator of a fraction never equal to 0?
Because you can never divide by 0.
Very good. So the denominator of a fraction must never be 0 because you cannot divide by 0. All right, now, so once we got to rational numbers, we're now able to solve the equation ax plus b is equal to 0, where b is not 0. So the solution to that is what? Is now possible. Before the introduction of rational numbers, the solution to that was not always possible. So for example, if I have, let us say, 2x minus 3 is equal to 0. Sorry, let me use a different ink. If I have, let's say, 2x minus 3, let's use minus 3 is equal to 0, then x would be equal to 3 over 2. So if all we have were integers, we would not be able to come up with to have a solution for this. All right, let me let in Keisha. We would not have a solution to this equation because the solution for this equation is not an integer. So you find that every time there's an introduction of a new type of number, whenever there's an introduction of a new type of number, it allows you to solve, let us say, an equation that you were not able to solve before. So with the introduction of rational numbers, we're now able to solve equations of the form ax plus b is equal to 0. And all of this now that we're going through here is to build up to the idea as to why was it necessary to add another set of numbers and call it complex numbers. Now, with rational numbers, however, you can't solve. So if we had stopped at rational numbers, you would not have been able to solve the equation x squared is equal to 2. Can anybody tell me why? Let me say again. If we had stopped at integers, we would not have a solution to this equation. Can anybody tell me why?
Sir, because integers cannot, if you had an integer as x, then you would not be able to get a negative number, or it would not be able to equate to a negative number.
No, man, integer, remember, no, integers are a negative number, no, so it's not negative. Negative is not the issue. Anybody else want to attempt? Why is it that?
Not have a fraction?
Excellent. The solution to this equation is a fraction, but integers are not fractions. So if our understanding of numbers, if the evolution of numbers had stopped, if the evolution of numbers had stopped at integers, we would not be able to solve equations like this because the solution of this equation is not an integer. Now, with that in mind, if we had stopped at rational numbers, why would we be able to solve this equation? X squared is equal to 2. If our evolution of numbers had stopped at rational numbers, would we have been able to solve that equation? X squared is equal to 2. I'll take anybody's answer.
No, sir, because it does not deal with powers.
All right. Thank you for your contribution, but not the answer I was looking for. Anybody else? First of all, what is the solution of this equation? What is the solution of the equation x squared is equal to 2? Ladies? All right, let's not spend
Sir,
too much
you
time.
find the square root of 2.
So x would be equal to the square root of 2. What do you know about the square root of 2? Anybody?
It comes in the form of a decimal or a rational number.
All right, the issue is you would not be able to solve this if our evolution of numbers had stopped at rational numbers. We would not be able to solve this because the root of 2 is irrational. The root of 2 is irrational. It cannot be expressed as a fraction. Also, the root of 3 is irrational. Pi is irrational. So in other words, the evolution of, it is necessary for the evolution of numbers so as to allow us to solve different types of equation. So let us say we were happy going along with our understanding of numbers until we came across a problem that we could not solve with our current level of knowledge. And at that point, something else has to be introduced. So irrational numbers. So once we got to irrational numbers, which is the symbol for irrational number is Q with a dash over the top. And essentially an irrational number is just simply a number that is not a rational number. A rational number is a number that can be expressed as a fraction. So an irrational number is a number that cannot be expressed as a fraction. So with the introduction of the idea of irrational numbers, we can now solve equations like x squared is equal to 2. So once we introduce irrational numbers, now the union or the grouping of real numbers and the grouping of what rational and irrational numbers were now called what? Real numbers. All right, so we are real numbers, and up until CXC, that is where we would have stopped. We would have stopped at the idea of real numbers. But now at this level, now we need to move on. Now, at this level, we have this scenario to deal with. The solution of the equation x squared is equal to -1. Now, if our evolution of numbers had stopped at real number, we would not be able to solve that equation because the answer for this would be x would be the square root of -1, and the square root of -1 is not a real number. The square root of -1 is not a real number. So therefore, to solve this, we had to introduce what is called an imaginary number. And then now, when we group imaginary numbers and real numbers, the grouping of those two types of numbers is called a complex number. So under imaginary numbers, symbol I, x squared is equal to -1, that's that level. So x would be equal to the square root of -1, and the square root of -1 is I. So in this new mathematics, the square root of -1 is I. And obviously, it means that I squared would be equal to -1. and complex numbers symbol C is the union of real numbers and imaginary numbers. Any questions, guys?
No, sir.
All right. Are you taking notes or can I move on?
Sir, we're taking notes. Could you just go back to the beginning?
I have no problem. I'm going back up. And if I'm moving the screen too fast, you must always tell me.
Excuse, oh, I was just going to remind you that your recording went off.
Okay, I'm gonna put it back on. This says the set of real numbers is a subset of the set of complex numbers. So there we have here, R is a subset of C. So every real number is a complex number with an imaginary part being equal to 0. So a complex number, let us say complex number Z, is of the form, let us say X plus IY. I think it's probably written on the next page. Now, where X is the real part and Y is the imaginary part. All right. Now, if the imaginary part is 0, it means that your complex number is just a real number. And if the real number part is 0, it means that your complex number is a pure imaginary number. All right. So here I have a little diagram showing you the set of numbers from natural numbers. I mean, maybe from about grade 3 or about grade 3, you would start get introduced to that. Whole numbers, integers, rational numbers, irrational numbers, which all come under the set of real numbers. And now you have real numbers and imaginary numbers, which together make up the set of complex numbers. All right, so this diagram is just showing you how the thing works. All right, so let's move down to example 1. All right, it's not exactly example 1, but it's just a little idea. And I'm going to do this so you don't have to worry about it much. Just checking the color ink. It says use the quadratic formula to solve this equation. So the equation is x squared plus x plus 1. And I'm just showing you the idea of the complex number. How does it work? Or how the idea of I works as it relates to solving a quadratic equation with imaginary roots. All right, so if I'm using the quadratic formula, it is x is equal to minus b plus or minus the square root of b squared minus 4ac all over 2a. All right, that's the formula. A is 1. Everybody should know that. A is the number in front of x squared. It's 1. B is also 1. B is the number in front of x, or the coefficient of x. C is the constant term, which is also 1. So if I put that in, I'm going to get minus 1 plus or minus the square root of 1 squared minus 4 times A1 times C1 all over 2 times A, which is 1. So as I said, I'm just showing you how with the introduction of I'm able to solve a quadratic equation with imaginary roots. So this is minus 1 plus or minus the square root of 1 minus 4. And this is all over 2. this is minus 1 plus or minus the square root of minus 3 over 2. I could write this as minus 1 plus or minus the square root of 3 multiplied by the square root of minus 1. And this is all over 2. Anybody have any difficulty with that?
No,
Anybody?
sir.
No? Okay, good. All right, no. So this becomes no. This is equal to minus 1 plus or minus the square root of 3. And of course, the square root of minus 1 is called I. And this is all over 2. So therefore, my solutions are x is equal to minus 1 plus root 3i over 2, or minus 1 minus root 3i over 2. All right. So without the introduction of imaginary numbers, solving this equation would not have been possible. All right. So let me just line it up so you can write it down. I mean, as we move forward, you will get an opportunity to do your own working out.